Can we go?
Why the attendance is short today?
We have an agent for the other course. Session.
Did we discuss the idea of difference between interpolation and extrapolation? Today we'll discuss this idea. This is a very interesting idea and a very critical idea for regression, especially. Okay, I want you to turn off your mobiles and keep your mobiles in the pockets. Ahmed, this other exam is actually business exam. Business? Hussein Jafar. Saud Fahad. Abdullah Suleiman. Salman Fahad. Muhammad Ahmad.
Yes.
Muhammad Ahmad Al Khayyat. Salman Abdullah. Faisal Fahad.
Yes.
Muhammad Abdullah. Fahad Khalid. Abdurrahman. Muhammad Suleiman. Muhammad Ahmad. Hamid. Haytham. Farooq. Ibrahim.
Yes.
Yusuf. Hussein.
Yes.
Hassan.
Yes.
Abdul Hadi.
Yes.
Ahmed. Jawad.
Yes.
Ahmed. Abdulaziz.
Yes.
Ahmed Assam. Vishal. Saad. Fahad.
Yes.
Yes. Abdulaziz.
What's the policy for the absent?
What do you mean by the policy? When you are absent, you are absent. You go beyond 9, you get W. Not W, sorry, DN.
No grade deductions for absent.
Again?
Grade deduction.
Yes, of course, there will be grade deduction.
Yeah, that's what I'm asking about. Is there a criteria or something?
Yes, minus 10% for every absence. So if you have 9, you will be graded out of 10.
5 absences already.
Yes. Now we are in week 8, right? Okay, today we will discuss the idea of interpolation and extrapolation. By the word, what do you think? What is interpolation and extrapolation? It's the same idea that the word explains. What is it?
Expected inside the interpretation outside the bits.
Hope we'll be back. Now, interpolation is kind of prediction when you are predicting within the available domain of X. For example, I have this data 2, 2, 3, 5, 9, and 15. And against that, I have Y's 22, 24, 19, 19, 16, and 12. Let us say this is my data. And based on this data, I fit the regression y hat equals beta naught hat plus beta 1 hat times xi. And after fitting this regression, if I use it for estimating the mean of y, or I use it for a single value of y when x is, let us say, 10. I will plug 10 into the equation and I'll get y hat or mu hat, or I'll get the prediction interval or the confidence interval for mean. This whole thing will be called interpolation. Why? Because this x naught equals 10 is within the available domain of x values that I have. The x values I have, they range from 2 all the way up to 15. So if this value belongs within that domain, you are interpolating. And as far as regression is concerned, interpolation is considered much more safer than extrapolation.
Even logical, so extrapolate.
It doesn't seem safe to extrapolate because you never know, after 15 the relationship changes direction. You never know, and you will get a completely different value of y hat. Currently, what I see from this data is that when x is between 2 and 15, the relationship between x and y is a negative linear relationship. By the look of the data, it seems negative. But you never know, after 15, the relationship becomes positive, it becomes quadratic, it becomes logarithmic. We don't know because we have not observed. We haven't observed anything outside 15 and 2 to 15. So what we have not observed, it is better not to comment on that. So if I do the prediction for x naught equals 10, this is called interpolation. And if I do it for x naught equals 20, this is called extrapolation. And doing extrapolation in regression is very, very dangerous. We prefer to avoid doing extrapolation. Now the question is, yes.
How do we do the time series analysis? We can't extrapolate.
Time series analysis is something different. In time series analysis, you are basically scaling the variables back, and there is correlation between the values. Here, the assumption is that there is no correlation between the values. That's a completely different model. The values are correlated. So from the next value is generated from the previous value. You see, in the model yi is a function of yi minus 1. I don't know much about the time series, but yi is basically a function of yi minus 1, right? So this is a sequence of observations which are correlated with the previous. It is completely different from the regression. We have independent observations here. Also, there for one time point, you have one observation here. For x equals 2, you have a complete distribution of y. Now, my question here is that we say we should always try to avoid doing extrapolation in regression, but the question is, how do we know whether what we are doing is interpolation or extrapolation? It's very easy to judge in case of a single predictor. But what if I have two predictors? How do I know whether what I'm doing is interpolation or extrapolation? Let's say I give you another predictor, x2. And that x2 is here. 17, 20, 29, 31, 29, 28. And then I give you x1 naught equals 22 and x2 naught equals 14. Is this interpolation or extrapolation? We don't know. That's the question. Why? That is the question, and it is a very, very important question. Now, let me change this a little bit. Yeah. Here. So apparently this seems like this is interpolation because x1 naught is within the domain of x1, x2 naught is within the domain of x2, correct?
Yes.
but it is not interpolation. I'll explain to you why. Forget about y, the variable y. Interpolation, extrapolation is coming from what? The predictors, right? You have to see if the available time point, that the value of x naught, does that belong to the available domain of x's or not? Now, let us see when I plot x1 and x2 against each other. The first value of x1 is 17 and x2 is 2. So let me say I start with 17 here and I go all the way up to 38. And here I start with 2 and I go all the way up to 15. Okay, so when x1 is 17, x2 is 2. So there is a point here. When x1 is 20, x2 is again 2. So when I have 20, it's 2 again here. When it's 26, it's 3. 26 is here, so this becomes 3. And when it is 31, it's 5. 31 becomes 5, let us say here. And 29 becomes 9. 29 becomes 9 here. And 38 becomes 15. 38 becomes 15. This is the domain. This is the domain of x1, x2 that we have. If I represent this domain by a circle, this is a domain like this one, correct? Now, the new point I gave you is where? X1 is 32 and X2 is 14, not 14. No. Let me make it opposite. P. Here. Now, this specific blue point, it is within the domain of x's. If I draw the domain of x's, it is within 2 to 15. It is within the domain of y. It is within this square, but it is out of this oval shape where the data are available. It's like an outlier. So the available data is available. It's given in that black oval shape, and this point, although it is within the domain of x1, it is within the domain of x2, but still it's far from the given data. Principally, this should have been called extrapolation. It is extrapolation, but there is no way to judge it. Is there? There is. For example, you do a very hard work, you create a two-dimensional graph, and then you try to see the new point, it's out of the oval shape. You come up with argument that this is extrapolation. What if you have three predictors? Will you draw a three-dimensional plot and make a three-dimensional oval and try to see if the point is within? What if you have four predictors? You can't do. We need a general procedure to get to know that whatever we are doing for the new observation, is it interpolation or extrapolation? Now, this I will explain with the help of simple regression one predictor, but this is in the same spirit applied for any number of predictors. The procedure goes as follows. For x1, the data are available up to what? From 2 all the way up to 15. Is it correct? It is correct. Now, what is the center of 2 to 15? Somewhere here. Correct? The center. In case of single variable, I'll talk about center. In case of more variables, I'll talk about centroid. So the center is somewhere, it's not 8.5. It will be based on the values, the magnitude of the values, 2 plus 2 plus whatever. So the center will be somewhere around, let's say 8.5, not exactly 8.5, but it will be around 8.5. Now, my question is, what if I take the distance of each value from the center and square it? All the distances will go to the positive, correct? I'll take xi minus the center whole square, right? And then I'll see where is this distance squared distance maximized, right? It will be either maximized here for x equals 2, or it will be maximized at 15. Because the centroid is in the center, I think it will be maximized at both. Somewhere close to 2 or somewhere close to 15. 15 minus 8.5 whole square, 2 minus 8.5 whole square, they will be close to each other or maybe equal to each other. So this distance is maximized at the edge of your domain. Correct? Now, if I have a new value x dot, and for that new value, I find this distance again, this new x naught minus the 8.5 whole square. And if this distance is more than the maximum of that I found before, it's extrapolation. And if this new distance, the squared distance from the value to the centroid, if it is less than the maximum available squared distance, it's what? It's interpolation in terms of single variable. In terms of more variables, we need to get a mechanism that gives us the distance of each point from the centroid. What is that? Do we have anything like that? We need a measure of squared distance of each x from the centroid of X matrix. Do we have something like that? What is that? Magnitude of predictor
Of the vector.
magnitude of the vector. I'm talking in terms of multiple now. Do we have any measure that gives us the squared distance of each value from the centroid of X matrix? This is the measure. The popular H matrix, hat matrix. What is this hat matrix? Where is the transpose, on the right or on the left? In the right. This is H matrix, and we said that the diagonal elements of this matrix are very important. What do they tell you? This is what they tell you. Each diagonal element of H matrix tells you the distance of that specific value, the square distance of that specific value from the centroid of X matrix. So if HII, the diagonal element of H matrix, if it is a big value, that means this value is far away from the centroid of the available X data. If it is close to 0, that means the value is around the centroid. Now the procedure is what? You will calculate all the HIIs for the available data. How many values will be there? These will be n values because this is n cross n. So the diagonal elements will be n diagonal values. You get those n diagonal values. They will tell you the square distances of each x from the centroid. Take the maximum of that. What is this? This is your critical value, kind of critical value.
Do we have the distance, the new points given?
This is your critical value. Now take the new point and call it x naught prime. And this x naught prime is what? 1, x1 naught, x2 naught, all the way up to xk naught. Correct? Put it into the H matrix and get H naught. This will be x naught into x prime x whole inverse x naught. Where should I put the prime? To the right or to the left? I'm going to put it to the left. Transpose. Go and think about it, why I put it on the left. This will give me a single value. This will give me a single value. This value is called H naught naught. This is the distance of this new value from the available centroid. If this distance is more than h max, what does that mean? That means the prediction you are doing is extrapolation. If it is within, you are doing interpolation. Any questions? Yes. No. We're not interested in minimum. Minimum means that the value is close to the centroid. Like in this data, in this available data here, if I have x equals 7.5, is this interpolation or extrapolation? It's right in the center of 2 and 15. I don't need to check for this one. I should be straight away sure that this is not extrapolation. We are not interested in the values close to the center. We're basically squaring. So forget about the negative side. Negative side is gone when you square it. There will be no lower limit because you are squaring the quantities. You are squaring the distances. Look at the definition of H matrix. There is x here, there is x prime here. You're squaring basically. So this is kind of a square distance from the centroid. There will be no lower limit, only the upper limit. If a value is outside the upper limit, it may be an outlier from the right side or maybe from the left side. We don't know because we squared. We lost the information on the sign. So we don't know if it is extrapolation from the right or from the left. We will not know it. Now let us implement this thing. And for that, let me try to find a suitable data set, which has maybe more than 2 predictors to explain it in a good spirit. Yeah, 10.1, this cement data. No, H is basic H itself, not the difference between H not H max. H itself for any value, H is the squared distance of that specific value from the centroid. Let me try to explain this.
What is the formula of H?
Maximum of HII.
And how we get the maximum?
Get the diagonal entries and take the maximum out of those diagonal entries. The biggest value of the diagonal entries of H matrix. Let me try to extract it in front of you and then you will get to know, okay? The first thing I'm going to do is I'm going to call this thing as X. X matrix. And I think this is the only thing I need. I don't need Y. What will be my H matrix? N cross N. What is N? 13. So the first thing I'll do is I'll select a 13 by 13. So let me try this all the way up to 13. 1, 2. Again?
Can do it systematic. Next. For selected.
For me, no. So equals matrix multiply transpose of X matrix with X matrix. This is X transpose X, and then I'll take the inverse of this. This is the middle part now, X transpose X whole inverse. And then I'll multiply this one with the last thing, which is X transpose. And then I'll pre-multiply it with X. This is H. H will be N cross N. Now look here. The first diagonal entry is 0.55, right? This 0.55 is the squared distance, squared standardized difference of first value, this value, from the centroid. The second value is 0.33. This is the standardized squared distance of this value from the centroid. The third value is 0.57. This is the squared standardized difference of the third value from the centroid, and so on. Now the question is, how do I extract the diagonal entries? Call here HII equals, there's a command in Excel called index. What will this do? This will take this whole array of 13 values and pick this value from this array. Take the array of 13 values and pick ith value from this array, where I is this one. So from this array, it will pick the first value. From the second array, it will pick second value. From the third array, it will pick third value, and so on. So from the first array, it picked 0.55, then 0.33, then 0.57, and so on. So I extracted the diagonal entries.
Now we want them.
Now what you do is you just find the max of this equals maximum of this column, which is 0.7. Now for a new observation, if H0 is outside 0.7, you will be extrapolating. And if it is within 0.7, you will probably be interpolating. So let us try to write a new vector for which we are, let us say, predicting. And that new value, I'll try to write it within the domain and try to, let's say, I'll write this value. This value we know is interpolation, right? This is from the data. I picked it deliberately from the data. This is the new value. This one. I picked it from the data. So let me find H0 for this one. For this one, let me call this one to be X0 prime. X0 prime, and from the formula, I'll change
Calculation because it's moments and
it is supposed to be interpolation because I'm picking from within the data deliberately. Why it did not give me a value? Cricket. Matrix inverse. Let me only take the middle part. Equal M inverse. Okay, this one is running. This one is M inverse. So
have the transpose at the beginning.
I should have what in the beginning?
The transpose of X0.
I should have the row in the beginning and column in the. So in the beginning, I should have a row which is X0 prime. And at the end, I should have the transpose of. Yes, 0.357 something.
Why are you interchanging? That's not like this.
Why we are interchanging? Anyone can answer. It's the way we are defining X0.
Okay, we find it there as a column, and now we find okay.
It's the way you are defining X0. So H0, you got it to be 0.37. Is it within 0.7? Yes, it is. And it will be exactly the same that you got for this observation. This observation is number 5, is it? This observation is number 5, if I'm not wrong. So your H55 will be exactly the same, 0.35 something, this one, 0.356 something. on the right side. Now, what if I make it instead of 7, I make this 1, and look, I changed one observation from 7 to 1, and this 1 is within the domain of x1. It's not outside the domain of x1. Immediately, what happened to h naught naught? 3 point something outside 0.7 by a big margin. So this is called extrapolation. So when you are doing extrapolation, you should report this in the results that we are doing extrapolation, and we should be very cautious about using this y hat. This y hat is not a representative of the regression line that we fitted, because the value for which we are predicting it does not belong to the available domain of the data.
What should we do then?
You should not do the prediction outside your
So I must find
like
data.
I should not comment on time series in this class because that is not my domain. I don't know about time series.
Then we should have data that's inside this,
Yes.
and then we make it.
Yes. We'll talk about this thing in the next chapter probably, that in regression there are two types of unusual observations. So one of them is good for your regression, one of them is bad for your regression. If you have a data of 2, 3, 4, 2, 3, 4, 2, 3, 4, and suddenly there is a value 15 in your data, this is obviously an unusual observation, right? But sometimes this 15 is good for your data, for your regression. We'll discuss this in the next chapter. This 15, sometimes it increases the domain of your data. The bigger the domain, more applicable is your model. Any question from this topic of identifying between interpolation and extrapolation? This was section, the only section that I missed in chapter 3, I think. The topic name is hidden extrapolation. Where is it? It's obviously after testing, confidence interval, prediction, multiple regressions as hidden 3.8, hidden extrapolation. I think they are applying this one on a different data. Here it is the joint region of original data explained in terms of two variables. And you will see all the explanation of H matrix here. We are done with the standardized coefficients, standardized regression, unit normal scaling, which we will rarely use. Unit length scaling, we'll use it very frequently, and so on. So let us start chapter 4 now. This is called residual analysis. What is this residual analysis used for? This is regarding the assumptions of regression that we have. What are the 4 assumptions of simple linear regression model? Linearity of the relationship between y and x's. Independence of what? Residuals, yes, not residuals. Errors. Independent of the observations, that means each row of the data is independent of the other rows. Each row, or you can say the epsilon corresponding to that one is independent. So each row of the data, it's not the independence of y and x's. We want them to be dependent. That's the whole spirit of the regression, that y is dependent upon x. It's the independence of y2 with y1, y7 with y1, y9 with y1, x10 with x2. So it's the independence vertically.
Some assumptions.
Finish. Normality of errors. We are assuming each and everything that we did in hypothesis testing was relying on the normality of errors. If the errors are not normal, what will happen? Let me take you back. Week 3. We developed, look here. We said that beta 1 hat is a linear combination of y, and because it's a linear combination of y, beta 1 hat is normally distributed, right? And we said that the linear combination of normal is again normal. Now, how are we concluding that y is normal? Epsilon is normal. If epsilon is not normal, y will not be normal. If y is not normal, beta 1 hat will not be normal. If beta 1 hat is not normal, the resulting statistic will no longer be t. The statistic you defined for testing beta 0 hat, beta 1 hat, they are t. It's only t if it is a combination of normal and chi-square. And if the original epsilon is not normal, none of these analysis techniques can be applied. And the last assumption is what? Someone was saying multicollinearity is not an assumption. It's a problem, but not an assumption. What is the fourth assumption? Equal variance of yi for each level of x. What does this assumption mean? Sigma square is constant at each x. You have a complete distribution of y. For all those distributions, the dispersion in y is same. The spirit of this assumption is explained, I think it was week 2 or maybe 1, is explained in one of the diagrams. Where is the diagram? Probably week 1. Here in this diagram. You see, we are trying to explain here that for each x, there is a complete population of y, many values of y. And for this each population, the amount of spread in y is same, called sigma square, denoted by sigma square. So if for instance, you have the data or the actual variables, something like this, for x1, y's distribution is like this. For x2, it is like this. For x3, it is like this. For x4, it is like this. This is not constant variance. As I go along the x-axis, you see the amount of spread in y is increasing. So this is a violation of assumption number 4. Yes.
The assumption is violated. The estimated value will still be valid.
If the assumption is violated, the estimation is still valid. We are not assuming anything until the estimation phase. The assumptions come into the picture when we draw the distributions of the estimates. And those distributions are used in inference, in testing hypothesis. This assumption is sometimes referred to as homoscedasticity, equal variance. The opposite of this one is called heteroscedasticity. The failure of this assumption is called heteroscedasticity. Sometimes in the book you will see heteroscedastic variance, which means the variance is changing over the next level of x. Now, all these assumptions apparently it doesn't look like number one belongs to epsilon, but this also belongs to epsilon. All of these belong to epsilon. All of these assumptions are about the errors. The last assumption is that the variance of error for each level of X is same. This one is that the distribution of errors is normal for each X. This one is saying that epsilon 1 is independent of epsilon 2. Epsilon 2 is independent of epsilon 3. Each epsilon is independent of the others. This one is saying the relationship between y and x is linear. This is indirectly putting a constraint on epsilon because epsilon is nothing but a difference between y and x's. So all these assumptions are on epsilon. To study the impact of these assumptions, we will study epsilons. And because we do not have epsilons, what we will study is their estimates, which are errors or residuals. So this whole residual analysis will be based on EIs. EI is the difference between Y and. For checking these assumptions, you will be using the residuals. Yi minus Yi hat. Now, before I go on to the residual analysis and checking the assumptions one by one, there is one thing in regression called an unusual observation, an unusual error, outlier. Now, the problem with outlier is if you have one outlier in the data, all your assumptions will fail. Just because of one value, all your assumptions will fail. The normal probability plot will not look good. The residual plots will not look good. Everything will be disturbed. In the background, you will think that the assumptions are failing, but it would not be about the assumptions. It would be about that single observation. By deleting that single observation, all your assumptions may come back to normal. So before we go into the details of residual analysis for checking the four assumptions one by one, it is always good to get to know if your data are free of outliers. If there are, screen the outliers and then go for the residual analysis. So before I go into the discussion of residual plots for checking the assumptions one by one, I will discuss how to get to know that this is an unusual residual called outlier. To get an idea about whether an observation is an outlier or not, what is the most popular method? Box plot, even before box plot. Z-scores, Z values. You have the Z-scores. Box plot is a kind of robust, more robust and much better, and it was proposed after a very long time since the proposal of Z-score. Z-score is the oldest and most commonly used method. Now what we are going to do is we are going to propose the same thing with EIs. We are going to convert these EIs into Z-scores. And we'll see if that Z-score is within plus minus 3 or not. If it is, it's a usual observation. We hope it is a usual observation. If it is not, we hope it's not an unusual, it's an unusual observation. So how do we convert this EI into Z-score is, what is the mean of EIs? 0. So I don't need to subtract the mean. Clear? A Z-score for EI will be EI minus the mean of EI divided by a Z-score should ideally be, it should be EI minus the expected value of EI over variance of EI square root, correct? And we know that the expected value of EI is 0. So it should be simply EI over variance of EI square root. That's what ideally a Z-score should be. Now, do we have the variance of EIs? We don't have. That's the variance of epsilon. We have the variance of epsilon. The variance of epsilon is sigma square. Correct? And we have an estimate of this sigma square, which is what? MSE. So if you just take MSE and you plug it in here, this will be a very, very rough approximated z-score, where you are not putting the exact variance of EI, you are borrowing the variance of epsilon from there. Again, I'm not calling it ZD, I'm calling it D. Just using, yeah, the critical values you can use T and Z, they will be close to each other like 3 or. Now, what's the problem here? I'm not using the exact variance of EIs. I'm borrowing the variance, estimated variance of epsilons. This is the first scaling technique for the residuals called standardized residuals. The second one will be where I put the exact variance of EI. This one is called studentized residuals. And where do I get the exact variance of EIs? I will tell you in the next class. I will derive it mathematically, the exact variance of EIs, and I will plug it instead of MSE. If you have any question from today's class, you can ask, otherwise you're free to leave.
About the assumptions, the assumptions is what?
Again,
Before assumptions, like the assumptions.
which assumptions?
Before assumptions. Assumptions of something.
About the model.
We are making the model.
Practicality of the model. The model is only applicable if these assumptions are true about the model. If they are not true, all your hypothesis, test, inferences, they will be wrong.
They have the same assumptions of the t-test when you have a small sample.
No. That's a completely different thing.
I find them to be the same.
No. It's completely different. Completely different. The objective there is completely different.
Yeah, the objective are different, but I mean the assumptions themselves.